Okay. Data engineering. Any of you here already data engineers or data professionals of some kind, analysts, scientists? So, interested in potentially moving to data engineering as a profession? Well, I'll see if I can do it. Yeah. Okay. Good. So I'll see. So part of what I'd like to do, I guess, is give you a good impression of what data engineering work is like. What's been my experience working in data engineering? What's the kind of, I'm not going to linger on the history too much of data engineering altogether. I did live through it, so I'll focus on the parts that I have experience and what it feels like, what it's like now. Just quickly on the title, I personally really enjoyed there is a SQL function name called coalesce, which you can pass an array of values to it and it'll return to you the first one that's not null. And they could have gone with a very practical, pragmatic word like they have all over the rest of the SQL standard with if null, not null, next null, if, or whatever. But they chose to go with coalesce, which is this sort of poetic, nice word of like imagining this fog of values that you're searching through and then you coalesce something out of it into this one value that you want. I mean, in the end, it's just an array and it gives you the first not null one, and you should be careful about using it because you don't know what you might actually get. But I like the keyword, and as a professional together, I feel like it's a bit of a metaphor for data engineering in general, where data engineering typically fits into an organization where, especially in larger organizations, they might have data silos all over the place, they may be generating all kinds of business data, and they want to go into more detail, they might want to ask questions that span many of these data silos. They might want to ask questions that requires a lot of data integration, and there's something coalescing about that whole exercise. And it gets very messy, so hence messy coalescing. So just very quickly about me, I've been working as a consultant data engineer for a few years now, primarily on AWS, primarily greenfield projects, also a lot of conversion of existing projects in cloud-based data engineering platforms to enable data analytics and to enable deep learning and AI platforms as well, so touched on MLOps, that kind of thing, and if there's any questions about that, if there's no time at the end, feel free to approach me and talk about that. Previously, I also had some time to think about data science. I didn't actually end up doing a lot of data science. A lot of organizations think they want data science, they try to bring in data scientists, and then they figure out that they don't have anywhere near enough of the structured kind of data or the volume of data that they might need to actually be able to do with data science. And that was my experience, and so I ended up making a lot of really nice dashboards, doing a lot of really nice analytics, but very little sort of model development in data science. But originally I studied energy engineering, so classical engineering, thermodynamics and structures and so on, that kind of thing. And actually, as it happened in my consultancy work now, the first project I worked on was on for a business that had loads of massive grid-scale solar plants across South America. And they wanted to bring all of that data together into one platform and do some interesting regression modeling to assess whether different plant components are operating at the level that they should be based on that past data. And that was really fun because I was able to come into that project, and I was more of a junior data engineer in that context, but I knew everything about the actual data that was coming in because I had previously engineered, designed large solar plants. So in brief, what we'll talk about, obviously, we'll talk about what is data engineering, what is data, what is there to be engineered about it, right? I mean, Excel is great, why go beyond that, right? And to be honest, for a lot of people I say, don't go beyond Excel. It'll just cost you a lot more, and you won't be any happier. And then we'll quickly talk about some of the other roles that are related, and that there can be some confusion about. And then I do want to cover, I suspect we'll skip through a lot of it, but I do want to cover some of the, if you do want to enter the field, or if you collaborate with data engineers, what kind of words do data engineers throw around, what kind of problems do data engineers mostly think about, and therefore what's worth being aware of, like warehouses, pipelines, data lakes, and then when it comes to data modeling, how we think about table design and so on in databases. And then I'll touch on modern data stack as it is now. So what is data engineering? So it is a process. It is a process, and it's primarily about data infrastructure. So data engineering is not data analytics, right? I mean, a lot of data engineers do end up spending a lot of time with data, with tabular data, with spending time in tables, troubleshooting data issues. Data engineering really is about the infrastructure, and then originally that may have been just one piece of infrastructure, one really big central data warehouse. Nowadays, especially on the cloud-native solutions, a data platform that we might deliver in the consultancy will have 5, 10 moving parts of different AWS services that all have to communicate to each other, and all have to continue working. Hence, there is a significant sort of engineering component to that. For a lot of businesses, data is just and the space in which data engineering would fit in is just a cost center in the business in terms of they just facilitate the analytics and the reports bubbling out to the people who might be interested in that information. But then obviously there's other kinds of businesses, the FANG companies and the Googles and the Ubers and so on. The data that their applications generate and the real world data that's coincident with that data that their applications make is crucially in the loop in the algorithms all the time, changing what the users see and changing what's being pushed out. And again, I haven't worked with that kind of stuff yet. I'm mixed feelings on whether I want to. It would be nice to be paid as much as they get paid, but there's different kinds of headaches. If we think of that as a kind of continuum there, I really like the bit in between when people take the data work seriously, they're really interested in what's coming out of the data function, and then they do some experiments in the business on that in a kind of agile way. You know, this is what our data is showing us about our business, let's try some interesting things there. And then let's see what data comes back, and then iterate on that, right? Rather than just doing this reporting that maybe some C-level executive will read, maybe not, who knows, but there's a lot of businesses where that happens. It's worth not hiding from. So, just linger for a second on data, digital information, right? Obviously, a lot of businesses will also have physical information. The previous data science job I had was actually for the London Gazette, if anyone's come across it. So this is an institution that's been around for several hundred years. They're still in the process of digitizing a lot of their really old stuff that went out in newspapers. It's like the legal notice board. And so really interesting opportunities there in terms of what they could do with that information, but typically we're talking about information encoded in some digital format. And in a business, this kind of information comes from many, many sources. So if you're a very small business, you might just have your operational databases about your application. You might have your MySQL database or Postgres or whatever. You might have a NoSQL database, and you have your customers details in there, you have your orders details in there, and so on. And all of this becomes, when you're really small, it's not a problem for a lot of people that have to make some decisions on that data. Just ask, you know, how many orders did you make last month? How many people go partway through the order process and then stop for whatever reason? When you're small, you can run those queries on that operational database and get those answers back, and it's not going to hold anything out. When you get bigger and when you have a business that actually, let's say even microservices first or something, and you have many, many databases, suddenly integrating data across these sources becomes an interesting challenge. But also, of course, many businesses have many SaaS platforms that they integrate with to facilitate the business, Salesforce, Shopify, so on. And so again, when we talk about data, we're talking about all of this information that exists throughout the business that a business may want to ask questions about. And of course also third-party data that your business may not be generating in, but maybe again coincidentally your activities, and you want to integrate that into the questions and answers you may have. So the questions being obviously, how is the business performing? How is it likely to perform in the future? So some kind of predictive sense, some kind of budgeting. What can we do about it? And obviously pretty much most of the time it's about, you know, what gets our customers to spend the money. So again, why do we need data engineers in the mix? You know, we have all these platforms, we have these databases already. Typically, in most businesses, you know, where does the data engineer come in? And it really comes into the fact that because so many of these questions span these data sources. So if you want to ask about how much business did our latest marketing drive generate, you're not going to get that answer back in one platform. Typically not. Maybe there are some more fancy integrated platforms, but even then, typically they won't give you the full answer. If you want to ask about customer conversion across many channels and so on, you're going to have to span these sources of data, and you won't be able to combine them in the SaaS platforms that you have or on your operational databases. And also, you may be able to do some analytics on things like Google Analytics and Shopify and so on, but it may not address some specific questions, specific need that you have. So that's where a data engineer comes in to pull that data out from all these different sources, put it into one central location, allow you to query across all of these different things, and ask more interesting questions. But again, this is where the engineering part comes in. Doing that work is not straightforward. The data comes in many different formats. The APIs are very different. Often, if you have an API on a platform at all, some platforms will just have an export to Excel option, and you'll have to be okay with that. If you have good data engineers, they might be happy to create a process for you where you press that export to Excel, you drop it into some AWS S3 bucket, and it's a process that kicks off to get the data out of that and then load it to a database. That may be your only option, and again, you need the engineering effort in that context to help with the process. Sorry, just looking for my water. And then data varies in quality across sources and in time. So again, that solar project I mentioned, the South American company, we've got this massive API integrating data from all of these sources over their systems, and it would just send us nonsense data every now and then. It would just send us, we're expecting numericals on particular fields, and they're sending us strings and various other things, and you just have to deal with that at the level of pulling that data in and validating it before it goes in. You can't automate a lot of it. And then over time, when you have started your integration effort and centralized analytics function in that way, more challenges start cropping up with, we've integrated similar kind of data from many different databases or different SaaS products. When a new person comes onto the business and they ask, where can I find the latest leads information about how many people are in the sales loop, suddenly there's 5 different data sets for that, and you need to have a decent catalog so that you can point people to the right place. And that's a really hard problem that's basically unsolved. It's all human effort. People have to maintain these catalogs. There's only so much you can do with cleverness and engineering. And then the real big thing in the end, really, with data engineers and what's typically associated with data engineers, especially in the data warehouse, is that data that you integrate into the central store typically needs to be reshaped a particular way for efficient analysis. Meaning that if it comes in adjacent data, so on, you wouldn't necessarily be able to do the kind of cutting and filtering on that data the way you might want to. So you need some people who have an understanding and appreciation for how to make certain kinds of data efficient to be queried on the platform that you have. So it's a combination of not just data engineering theory, but also knowledge of the platform that you're on. And then obviously, you take all those challenges and then you add the reality that that data needs to be constantly refreshed, the new data constantly needs to be brought in, data quality issues crop up. Somebody needs to fix that and make it work again. So you need people on staff to do that most of the time. Again, if you're smaller, you can get away with a good set of any kinds of engineers to do that, but when you get bigger, you typically end up needing a specialist for that. I just wanted to cover a little bit so some of the other related roles in that space, right? So data engineers are not analysts, of course, data scientists, but obviously the domains overlap a little bit. But the crucial, really, distinction is that, again, like I mentioned, data engineering is about the infrastructure. And some of what I'm going to describe here are my opinions rather than categorical fact. But so data analysts typically have the best business context and understanding of a particular department and what data they want and what they're interested in. They typically have the strongest domain knowledge of that business if they've been there for a while. So even though there is sometimes a perception of analysts and scientists and data engineers having some kind of hierarchy or one telling the other what to do, it's really just kind of slightly overlapping domains and slightly different concerns. And people specializing in being the best data analyst should be respected for being the best data analyst they can be. They don't have to graduate into becoming a data scientist. It's not a progression like that. And data analysts, I like to think of it as a chief decision scientist at Google, Cassie Kozakov, talks about the key specialty of the data analyst as being their ability to generate inspiration from data that the business already has, right? So data analysts don't typically generate new data. They may do some predictive analytics and so on, but typically they deal in the world of what do we have as opposed to what would we like to see. Some of them are pressured into that, but their game should be knowing the tools, knowing the data, and getting to the right information really quickly. But obviously, and again, in a more complicated situation, they depend on the data platform that data engineers maintain. And data scientists is sort of is more advanced in some ways than data analysts in terms of a happy data scientist would be doing more statistical analysis on data, would be doing more hypothesis and A/B testing programs on a business, putting out some effort into the world, and then bringing back the data in about how did that succeed, did that work, did that tick up some metric, KPI, OKR, and so on. And data scientists should really be working with trying to be a bit more rigorous than a data analyst, whereas for data analysts at speed, and data scientists should be how certain can we be that our efforts made an impact of some kind. And then of course, machine learning models and iterating on machine learning products, and so their specialty ends up being could be machine learning techniques in the libraries. But again, like our personal experience, it's really hard to do any data science if you don't have access to data. And data that isn't constantly going stale, isn't constantly being questioned. Is that the right data? Do we know where it came from?
Can I ask you a quick question?
Yeah.
Just, are you suggesting so a data analyst is not actually someone who analyses the data itself or the implications of the data? They're more someone who analyses that the data that you have is useful for the purpose, so that when a data scientist comes to it, they can actually do that stuff and create a meaning out of it.
No, not necessarily. So I guess all I'm saying is you could get a lot more detail into that slide, right? But the data analyst, as in the key skill that the data analyst should hone is that they really know the data really well, and they can surface responses to any questions that business stakeholders or data scientists might have, right? So they can navigate that space really quickly, and they can tell you, hopefully, where that data came from and so on. But it typically wouldn't be for the data analyst to massage the message. I mean, it often is, again, they're pressured into doing that, but it shouldn't have to be. It should be a bit more objective. And the data analyst and data scientist efforts don't have to overlap or stack on top of each other. They often will because it's helpful. But again, we don't have to think of any kind of hierarchy that the data analyst feeds the data scientist, both of which operate on the platform. They can have independent streams of work, right? Focusing on different questions. So that's the data scientist. And again, this is kind of how I categorize it in my head, and having worked in the MLA and consultancy and how we split the work typically, but also seeing how many organizations that we worked with, how they split that in data teams, and what was helpful. And then just to mention as well that, of course, then the data engineers typically don't do the slightly more lower level cloud networking and lower than data infrastructure level management. That typically still falls onto platform DevOps and so on. Again, in the right context, you might have a really, really great data engineer that can do everything, really full stack top to bottom, but that's unicorn territory. And then the crucial other relationship is that in many organizations where the data effort is really dependent on the operational databases in the business, so what data the business is gathering is part of its selling and buying and interacting with customers. It's really important for data engineers, and they often do collaborate with the backend developers who are changing the databases, who are changing the tables, so that when those changes happen, that doesn't break a whole stack of reporting tables on the analytics side that some set of business stakeholders are expecting to see refreshed every day. So it's typically appreciated when the back-end developer gives the data engineering function a heads up, which doesn't always happen. There was a lot of talk over the last few months in the kind of data LinkedIn influencer space about this data contract idea. It's part of this data mesh idea that a lot of people are talking about. The idea being that you'd actually establish internally sort of fairly hard data contracts with the back-end developers, that internally the data engineers expect this data to come out this way. And every time you make a change, you need to verify that against this agreement that we have, essentially a data contract in that way. And in the data space, obviously everybody's really happy about this because all the data engineers are sick of their stuff being broken by back-end developers moving really quickly and servicing the need of the application and the users and so on. But then that breaks all the analytical stack. And so yeah, in the data world, everyone's really happy about that. But I imagine if I spoke to some of you here who are back-end developers, it would be like, you don't want to make these, like you already have commitments, to the front end and to other things, but parts of the business, why would you do another thing that slows you down in the business? So I imagine how that actually ends up materializing is, we'll see if anybody does it. I just want to throw in there, like, just if anybody's interested in terms of relative pay scales. This is Otter, by the way. I do enjoy that as a job search platform. Haven't succeeded yet, but it feels nice. It's new. But anyway, they have this benchmarking thing, and this is comparing a data engineer salary with years of experience with a front-end engineer, just as an example. It's pretty similar. And yeah, if you're pretty good, you can achieve 45, 60 with a few years experience, and then 60, 80 in the senior level. But obviously it totally depends on the organization. Again, I work in consultancy, so it's easier to have some of those pay conversations in consultancy because you're much closer to what you're being charged out and so on. Different functions would be different, but I wanted to throw that in there. Cool. Any questions so far, just in case? Yeah, go.
On the sort of data science, data engineering again. In the organisations you go into, how do you find that they're generally set up? Are they quite siloed? And in the different ways that they are set up, which have you found most effective in terms of like the actual output?
Well, so I think it's much more likely that analysts are spread across the organisation in different departments, and that's quite normal. And then data engineering is typically centralised, and I think that's fine. I think so. Again, mentioning this like data mesh thing, that a lot of the big the kind of executives who go to conferences will go, oh, data mesh, we've got to do that, right? So data mesh is interesting because, so talking about how to distribute this work, data mesh is interesting because we've talked for a long time about bringing this data in centrally into one data warehouse, and there's this key term that we use, which is single source of truth, right? We like this idea in the data world, in the business world, that we have these disparate sources of data, but we can bring them centrally into one location, and when somebody else from marketing data, we say, we have a single source of truth, go to that table. Data mesh kind of breaks that open again, and they say, put the data with the specialists, right? So have the marketing people have their database that they look after because they know the data. Have the salespeople have their database because they know and they look after it. And you'd have an analyst split that way as well. But what you then have is, you do still have a centralized data engineering capacity, but that's for providing the infrastructure for each of those distributed teams to do their best work, right? So it's hard to answer the question sort of very specifically, but in general, I think in a kind of perfect agile world, you would do right by the people that you have. So if you have people who want to build infrastructure, let them build infrastructure. If you have people who want to do data analytics, let them do data analytics, right? And have them integrate with the teams that care for that work, rather than bringing everybody in the middle just for the sake of it, right? And then finding that suddenly the departments that actually want to use that data aren't getting what they want because the conversations have been broken. So, okay, so talking about that, so let's run through some data engineering ideas and what kind of things data engineers talk about. So the word schema comes out a lot. And that's something I had to learn very quickly as I came in. So there's a schema, so we often talk about schemas at the level of database tables. So when we create a new table, we'll say this table will have these fields, and they'll have these types. There'll be an integer field, and there'll be a string field, and there'll be this. That's a table schema. But then there's also at the level of the whole database, there's schemas as namespaces for different tables. So we'll have a sales schema with revenue, commissions, and leads tables. And we'll have an ops schema with incidents, personal, whatever, right? Other kinds of tables. And data engineers are very comfortable just kind of using the same word in any conversation and expect you to infer from context. And then of course there's the formal sort of whole database schemas where you build the whole data model in one what typically is called an ERD, a entity relationship diagram, where you show these are all the different tables we're going to have. These are going to be their relationships, one to many, many to one. I'm not going to go too much into detail into all of that, but all of these words we use schema for, all of these concepts, and we're just kind of comfortable with that. And so just as an example there, ChatGPT generated that for me, which was nice. It did really struggle with this though. I kept asking it to draw another line between book and publisher, but it really couldn't do that. It kept drawing the lines in the wrong places or dropping one of the tables, so its ASCII art or capabilities still limited. So let's quickly run through when we talk about data again at the level of data engineering, what kind of data we talk about. So structured data, when we talk about structured data or imply structured data, we're talking about data from databases, tables, many of you would have seen this. So this is structured data. It's structured because, not only because we expect certain columns, we also expect certain data types. We expect certain kind of information at the level of literally what data is being encoded and saved in storage. And there's quite a lot of assurance in databases to ensure that the data remains consistent and as you expected. Semi-structured data, things like JSON, CSV, XML, Parquet, any format which may give you still a structure in the sense of keys and values and the expected keys you might expect, but don't enforce what particular type of data actually ends up being stored against that key. So you might keep downloading from an API for a certain kind of data, and at some point, some of the values change from strings to numbers, but you've got a Python script that expects strings, you're running some string method on it, it breaks. So a little bit less guarantees. And then when we talk about unstructured data, we're talking about free-form text, imagine, reviews, Twitter messages, so on. But also, and this is still relevant in the world of data engineering because there will be businesses that have a lot of this data and they do want to bring it into a centralized place and potentially do analytics on. So unstructured data also has value. It's much harder to extract, but it does have value. So, Yelp does all kinds of questionable things, but this is another questionable thing perhaps, but they'll look at the kind of reviews that are placed against the kind of businesses that are registered with them, and they will then draw implications on that when a new business of the same kind comes in, right? So they'll say, okay, this kind of business typically gets these kinds of reviews, these kinds of sentiments. We can infer something about what we think their likelihood of staying on the platform is for the next few years, and they can then, decide how hard to pursue them for a subscription fee to Yelp or whatever. Right. Let's get to the data warehouse. So our single source of truth, most commonly the central piece in many data organizations, and probably where sort of the original data engineers in the 70s and 80s came from. People whose sole job was to look after these central databases. And so the big thing about the data warehouse, what's good about it is it's inflexible in many ways, but what's good about it is that inflexibility typically leads to high quality data. It often also means that you have to spend a lot more effort up front to design a really good data warehouse and design a really good model for how you're going to gather and hold all this data. But typically that means that your data stays good for longer, but it is less flexible. And it will take only certain kinds of data. You'll struggle to put a lot of unstructured data in a useful way in a data warehouse. And then in terms of the modern, and that's what schema on write means in that context, is that every single time you want to write this data warehouse, it enforces a schema. It enforces a particular schema that you define in those tables. So if you want to write something to a particular table, it has to fit the recipe for that table. And then in terms of the modern data warehouses, where they are successful nowadays is because they're based on architectures in terms of the servers that run them behind the scenes that can scale out your query requests to those data warehouses across many, many machines to serve that query, split out that work, so they can be performant in the way that the warehouses of the 80s couldn't. And also column-oriented storage was a really big change. So compared to a normal database, I might have a moment to get into, but compared to a normal MySQL, Postgres, whatever, records are not stored individually on disk. The table data is actually stored in the columns. And so that means if you want to go to a data warehouse and change one record at a time, or some records spread across that table, it's going to be terribly unperformant, because you'll have to pull the whole thing, all of those columns, and you have to then change some of those values. So we don't do that with data warehouses. Data warehouses are typically, as much as you can, append only. And then if you do make changes to certain kinds of sizes of table, it's often much more performant to drop the whole thing and rebuild it with some of the new data you've put in, as opposed to trying to go through it. And we don't do indexes in data warehouses either. There's no indexing on these tables. There is some partitioning where the storage, so you can define some partition keys where if you say my data, I'd often like to join it by this category key of some kind that splits your product by certain categories. You can tell the data warehouse to also store those values split in that way, so that when you want to make changes to them, it only brings back those partitions into memory. But we don't do indexes because it's all stored in columns. So, no fun.
Can I ask a question? Why would you use column oriented storage?
So it's because it's analytics questions typically aggregate data. So you ask, how many of these do I have? How many, can you sum all of this? And so on. So you want to know all the sales you've done in a particular month. You'll eventually come down to your query result set will be some table with a long column that you want to sum up. So in a normal database, that would mean you'd have to bring back all the records and then only take out the one value you want to sum up. But in the columnar database, you just bring back that one column that you want to sum up. So it makes all of these things much more efficient. The analytical nature of the kind of SQL we run against data warehouses makes sense on columnar databases. But a lot of people don't do it right, so they get terrible performance out of their data warehouse. Is that good? Yeah, it also really helps with storage and compression. So if you store a column that is just Boolean trues and falses, you don't have to, if you're storing by record, storing that true or false again and again and again in every single record. Whereas if it's one long column that only consists of zeros and ones, trues and falses, you can compress that column much, much better for storage. So the compression that's available to you for storing terabytes and petabytes of data is much more efficient. And yeah, the big ones that, in terms of the good big data warehouses, Redshift, BigQuery, Azure have Synapse. I think Synapse is a little bit more interesting, but I've had less experience with that. Snowflake is the really cool kit right now that everybody wants to be using, and it is really cool in terms of they have a real separation of compute from the storage. So if you think back, I mean, a data warehouse, especially an on-prem one, was just a set of machines that was running some distributed bit of. You might have many hard drives that it's pulling data from, and then it has many CPUs for doing some work. But if you wanted to, it would be really hard to scale. Well, yeah, I'll drop that example. The point is, when you get to Snowflake now and the cloud experience, in Snowflake you can store as much data as you want, petabytes, and have no significant compute resources allocated on that account at all. So the amount of data you want to store and the amount of compute resources you want to have available to you are completely decoupled. And you can do things in Snowflake where you run some SQL query, and you know it's going to be a really SQL query that's going to have to crunch through terabytes of data, so it might take a long time. And so you say at the top of the file, I want to use the extra large warehouse that has 256 virtual CPUs, or actually I want to go for 1,000 vCPUs, whatever. You can say, I want to do that. You do your work. Now it's gone from 10 minutes to 1 minute because it's parallelized that SQL query across all these vCPUs. And then when you're done, at the bottom of that script, you say, turn off that warehouse, take all the warehouses. And it just happens in seconds. Like, their virtual capacity to allocate compute for different workloads is like next level compared to Redshift and even BigQuery. BigQuery is pretty good as well, but Redshift still fairly tightly coupled. If you want to bring on more storage, you kind of have to bring on more compute. There is more of a sense that you are really allocating machines behind the scene and they're still coupled together. Cool. So yeah, like I mentioned, data warehouse often, we talk about single sources of truth there. So let's talk about the data lake really quickly in comparison. So because last couple of projects I've actually worked on with customers, they didn't want to do a data warehouse. They wanted to do a data lake, and this is increasingly an option where all of their data is on, we call a data lake, which typically just means something like S3, if many of you are familiar with S3, probably AWS so object storage service. You can upload anything you like to S3. And so a data lake is like almost unstructured storage for anything. You can load anything you want into it. But there are all kinds of clever services that are coming online to query the data that's on S3. So even though you can kind of throw on whatever you want, there's all kinds of interesting services that are coming on that allow you to, for example, I mean, right at the start, for me, one of the things that blew my mind a little bit was that you can upload a whole bunch of CSVs to an S3 bucket, and then you can query them using the AWS Athena service as if it was a database table. So let's say you have some really big CSV with millions of rows in it, right? It's an export from something, some scientific data or something, and you want to run a SQL query against it. You can upload it to S3 and allow Athena to crawl that table first to infer its schema, what are the columns, what are the types, and then you can run SQL queries against it as if it was in a database, but it really is just a file uploaded to S3. So that's a simple example. These services get a lot more interesting and complicated. And at this point now, the formats that are available for you go beyond CSV and JSON and so on. There's formats like Parquet, Iceberg, Delta Lake, Hoodie, and so on, that actually allow you to do ACID transactional stuff on data in a data lake. It gets messy, but if you really want to go in that way and do that, it's pretty cool. And the primary advantage is that storage is cheaper in S3 compared to a data warehouse, compared to a provisioned large compute cluster of machines. So a lot of people choose to go that way, and the options are increasingly interesting for doing that. So yeah, I just mentioned some of the formats there, and they are file formats. They are file formats that, unlike CSV, aren't just text data separated by commas. They contain additional metadata, and actually at the level of how they store the data of the file, they also do interesting things like splitting by columns and so on. So again, when Athena has crawled something in your data lake, and let's say you've uploaded a 100 gigabyte CSV to S3, and you let Athena query it. If you select just one or two columns out of that CSV, treating it as if it's a table with a service, it will only scan the data in those two columns. It will not scan the whole file. It won't read the whole file and then discard the rest of the data. It will just scan those two columns. Sorry, maybe not if it's in a CSV, but if it's a Parquet file, then it will do that, because that file contains additional metadata that splits the data inside the file for that effect. And then just to mention, Lakehouse is an interesting thing. Databricks is a major provider who does this, which is basically kind of the best of both worlds. You have a whole bunch of lake data. It can be structured, unstructured, whatever, schema and read, but you have a warehouse-like experience. You can run SQL against this, similar to Athena, And you can have more structure on the plate as well. Yeah, I've really gone through my time, sorry guys. I'll just mention quickly, data pipelines, big thing data engineers talk about. That's the first thing that I was told when I inquired about what do data engineers do, having some analytics science background. They were like, they write ETLs. I was like, okay, what does that mean? Extract, transform, load, that means typically what that means is we write some script to go to a source, an API or a database, load that data into memory, transform it, and then push it into data warehouse. Okay, that's what ETL typically means, and that's what data pipelines typically mean. And there's loads of services in the space that allow you to automate this without you having to write these scripts. They already have connectors for all the really big SaaS platforms. And they have a connector for Shopify, they have a connector for Redshift. So you just connect the dots in their interface and it starts sending data across. And it's worth mentioning that there is a big thing about ETL versus ELT. So with storage getting cheaper, even in data warehouses, a lot of companies are choosing to extract the data from a source and just dumping it straight into the warehouse as is, even though it costs more to store it there, and then transforming it when it's in the warehouse. For a lot of people, that's a cost efficiency benefit. And dbt is a really cool current modern data stack tool for transforming data once it's in the warehouse. And if you're a data engineer or if you're a person who's interested in it, like being up to date on dbt, which is actually open source at core, they have a hosted SaaS version, but really, really cool tool. Like, I feel like almost nobody has bad things to say about it, except that it can get very expensive very quickly if you're dirty about it, which is the case for a lot of tools. But it's really, really good. And then I'll just quickly, and I'll finish there. Data modeling really is the thing I wanted to get to in terms of data engineers. When you think data engineers, you should be thinking about data modeling, which means that a data engineer is someone who can look at your organization and think about how am I going to take all your data, integrate it into a raw staging layer, process layer, and now ready for analytics layer. But then that ready for analytics layer as well, going further and actually thinking about the table design of how we can split certain kinds of data out and how they're going to relate to each other so that when the analysts run their queries, that's really, really efficient. That's really the key thing that a data engineer should be known for. And then final thing, I won't keep going, I'll just say the final thing, in terms of there's a difference between general kind of developers and software engineers and data engineers, that data engineering does tend to do less coding, does tend to do a lot more software integration between understanding warehouses and these SaaS platforms and these tools. But there's still plenty of coding, it's just not development in a sort of web developer or a platform developer, in a software engineer kind of way. So if you find that like you don't love the, product development as a software engineer, but you really like being part of the business organization that delivers value, potentially, you may want to consider data engineering, where you do get to do quite a bit of coding, but you get to mostly focus on finding really efficient paths for the right information to get to the right people. Cool, that's me, sorry.